In my today talks, I'm going to present VirtuOS, an operating system that makes use of kernel virtualization. Most general purpose operating system today use monolithic design. The design is shown on this figure. We have many system components running in a large kernel. It's a straightforward design. Components can communicate to each other, but it has a weakness. It has robustness problems in case of failures caused by the software bugs. For example, if an Ethernet driver fails, this may cause monolithic OS kernel failure, eventually leading to the entire system failure, and the only thing that we can do is to reboot the machine. The key problem here is that we are not protecting system components. So monolithic operating system run a number of third-party components, and a number of studies have shown that particular device drivers are more error-prone than other components, such as process manager or memory manager, which constitute core part of the system. To address this problem, system designers proposed to use decomposition and isolation. We split monolithic system into separate and isolated components. First, it improves modularity of the system, but most importantly, such system can contain faults, which allows for components to fail and be restarted independently, consequently improving reliability of the system. Decomposition is not a new idea. A number of approaches use it. For example, microkernel-based designs such as L4, Minix-free, retrofit driver protection schemes such as NUX, SUD, various user space file systems and device drivers, virtual machine-based approaches such as device driver OS or Zen driver domains. Despite the differences between these approaches, they belong to larger design space, and we believe that VirtuOS is a new point in the microkernel VM design space. The challenge is not to only provide decomposition and isolation, but to make decomposition flexible, isolation strong, while at the same time retain good performance, provide transparency to existing applications, and compatibility to systems code. We'll talk about characteristics of existing approaches and show how they reflect in VirtuOS. The design must be flexible to protect both low and high-level components. For example, on the figure shown on the top left, we have microkernel system. In the middle, we have driver protection schemes. They both can protect low and high-level components. For example, microkernel can protect low-level components such as Ethernet driver or high-level components such as TCP IP stack by running them in separate user processes. Similarly, driver protection schemes can use various kernel fortification schemes. Virtual machines can also be used to either protect the entire operating system, or as shown on the figure on the figure top right, we can protect low-level components such as Ethernet driver in a driver OS virtual machine. In VirtuOS, we protect both low and high-level components. To protect against faulty and malicious drivers, as well as from faulty device drivers, we must provide strong isolation. All systems usually provide protection domains to isolate resources. For example, they can provide separate virtual memory address spaces for system components, and this way they will be protected. Also, most systems provide privilege separation, allowing system components to run in less privileged mode. This way they reduce the chance that the failing component will adversely affect other parts of the system. Finally, recently some system makes use of device protections, so they can protect against faulty devices by using IMMU, which will remap DMA buffers and interrupts. In VirtuOS, we support all of this. So large amount of interdependencies between components make it actually very difficult to achieve good performance. For example, performance issues were an obstacle for all adoption of microkernels. Researchers spend a lot of effort to optimize IPC costs as well as to improve overall performance. In VirtuOS, we provide performance comparable to that of monolithic system, particularly for server workloads. For wide adoption of the system, we want to provide transparency to existing applications. For example, for example, microkernels, some microkernels spend the effort to provide an emulation layer allowing to run existing applications. Similarly, for wide adoption, we want to have compatibility with existing systems code. Reusing unmodified device drivers is simplified by use of virtual machines. In VirtuOS, we support both transparency to existing applications as well as compatibility with systems code. We will discuss VirtuOS architecture to illustrate how we address design challenges. We start with a monolithic OS. We run it inside a virtual machine on top of the hypervisor. We decompose and move components into separate servers and primary domains. Each domain runs in its own virtual machine. User processes will only run in the primary domain. Our primary domain will also run core components such as memory manager or process manager, which will facilitate management of the user processes. Finally, service domains will run a vertical slice of a given subsystem running both low and high level components. For example, storage domain will have file system drivers as well as storage controllers. We support both network and storage domains in our current prototype. The drivers in service domains can directly talk to hardware by utilizing hypervisor support for PCI pass-through and IMMU isolation. User processes can directly communicate with service domains by using direct system call dispatch mechanism. And this is a key feature of VirtuOS. To illustrate fault model of VirtuOS, we'll consider a failure scenario. For example, SATA driver fails, leading to the service domain failure, which may in turn result in a failure of the user process, which was using the service domain, because service domain keeps client state. But notice that other user processes are not affected. Primary domain, which runs core functionality, is still running. Network service domain is also running. So when we restart storage service domain, the system is fully recovered. To describe direct communication between user processes and service domain, we will talk about VirtuOS implementation. We have primary and service domain running modified Linux on top of Xen hypervisor. Primary domain runs user processes that are linked against modified C library. C library is dynamically loaded and provides binary compatibility to existing applications. To demonstrate direct communication between a user process and the service domain, I will describe read system call. First step that we need to take is to find out what service domain needs to handle this system call. Well, and the other thing is that we need to do it directly from the user space without consulting the local kernel. For read system call, we can use file descriptor. file descriptors are tagged with the domain, have a domain tagging, which will indicate what service domain will handle this given file. System call requests are submitted through the request queue resided in the shared region. A shared region between user process and service domains are established during the process initialization, and kernel worker threads in the service domain will pick up requests from the request queue and handle them on the behalf of the user process. So the C library puts a request into the request queue. Kernel worker thread picks up this request. Then essentially we will follow traditional system call handling mechanism by essentially calling sysread function. Sysread function will reuse existing mechanisms such as file descriptors associated with the kernel worker threads, user credentials, and signal contexts. So the request goes to file system, to SATA driver, eventually reaching the disk. When the I/O is completed, the data is copied out to the data buffer resided and allocated in a shared region. Meanwhile, user processes had to wait for result. So waiting requires that we deschedule current user thread and yield CPU time to some other threads. So we had to provide a lightweight context switch mechanism, and we chose to use end-to-end threading library, which runs multiple user threads on typically a small number of kernel entities. If a user level thread blocks, it will essentially do an efficient context switch directly from the user space. Going back to service domain, we note that service domain need to notify user process that the system call is complete. For this purpose, we share end-to-end libraries ready queue with the service domain so that it can directly insert thread ID into the ready queue, and this way the user thread will eventually be resumed. To ensure safe concurrent access by both user process and service domain, we adopted lock-free algorithms for all queues used in our shared regions. So another point to make is that service domains should not be affected by misbehaving processes. They will not trust data that they see in shared region. They expect to see queues in inconsistent state, and they will handle those cases appropriately. So kernel worker thread puts thread ID into the request on the ready queue. Eventually, user thread will be scheduled, and it will copy data out from the data buffer. Now, the use of data buffer implies that we have an additional copy compared to when we handle system calls locally. So we chose this design to avoid having to coordinate the memory management between between primary and service domains. So once we copied the data, we return from the system call. Now, end-to-end threading does not bring any benefit for single-threaded application. In addition, it may not always be possible to context switch to another user thread. So what do we do in this case? Well, we adopted a spinning approach. We will spin a little bit given threshold, anticipating that the kernel worker thread will produce result in a short period of time. So kernel worker thread handles the request, and eventually we return from the system call. Spinning is particularly useful for many core systems, and it allows to trade CPU time for latency. Well, if the service domain does not produce result within a given threshold, we need to request a notification and block the current user process. For this purpose, we go to the local system call, which blocks the current user process and waits for service domain notification. Again, service domain handles request, notifies primary domain, and wakes up the user process, after which we return from the system call. Now, it may sound good in theory, but does it work in practice? We build a prototype that implements network and storage domain. Our implementation runs many existing applications such as OpenSSH, MySQL, Apache, Firefox, and many other well-known applications. We run our system on top of Alpine Linux distribution, and our system is self-hosting. And what is wonderful also that we can run unchanged binaries. We believe that we were able to achieve our goal with respect to transparency to existing applications and compatibility to system code. The total number of lines, as you can see, is relatively small. We created failure scenarios to show how the ability to recover from failures and our isolation capabilities. We estimated overheads such as system call overhead, memory copying, process coordination. In my presentation, I will talk about memory copying overhead. Then we evaluated performance for multi-threaded applications that can utilize end-to-end threading, as well as purely multi-process applications that cannot benefit from end-to-end threading. Our system has 8 cores. We have 12 GB of RAM. We have gigabit Ethernet. In the failure recovery scenario, we demonstrate the ability to contain network domain failure without affecting a storage domain and a user process that uses it. We use Apache server, which will make use of networking domain, as well as disk copy program which will utilize storage domain. We report throughput as a measure of performance. Disk copy application is launched at instance 6. At instance 9, a remote client connects to Apache server and starts transferring data. At instance 29, we simulate a failed stop failure by abruptly terminating a network domain. And we can see that observed throughput of the client removes to 0, after which we assume that some watchdog program can detect this failure and restart network domain. VirtuOS currently provides support to clean up for failed domain, as well as to allow to terminate affected processes. So at instance 60, network domain is recovered, as well as Apache server, and remote clients continues to transfer data. We can see that during this time, storage domain, as well as an application that was using it, are completely unaffected by this failure. As explained in implementation, VirtuOS requires an additional copy for system calls that will transfer data. But on the other hand, VirtuOS uses a system call dispatch mechanism that avoids cost of exceptions usually found in normal systems such as Linux. In this benchmark, we write 16 megabytes of data using chunks of 32, 64 bytes up to 2 megabytes. We use TMPFS file system, and we compare performance of VirtuOS storage domain versus Linux performance, which uses exactly the same implementation of TMPFS. So in our results, we'll show a combination of memory copying with the benefit derived from the system call dispatch mechanism that we use. For block sizes less than 64 kilobyte, the benefits of system call dispatch outweigh the memory copying costs, and VirtuOS wins. For blocks larger or equal 64K, VirtuOS throughput reduces to, and throughput ratio becomes around 0.8. But it's worthwhile to notice that usually we don't have large buffers, and for example, core utils will use 32K blocks for file operations. We evaluated also performance using CPU-bound multi-threaded applications that can benefit from end-to-end threading. For this purpose, we ran OLTPC's bench to evaluate the performance of VirtuOS network domain. So we run remote clients that connect to MySQL server. They will send 10,000 requests. Each request will have 10 selections with output ordering. Our database completely resides in the memory, so we don't have any I/O. And the client will use multiple concurrent threads, each of which will issue requests sequentially. So in this results show that VirtuOS outperforms Linux mostly by 1 to 16%. Well, since multi-process application cannot benefit from end-to-end threading, we wanted to set up an additional experiment. And for this, we used Apache benchmark. We measure throughput for different request sizes up to 16K and for different client concurrency. So for 16K and larger, we were able to saturate gigabit link. For smaller requests, we actually see how performance degradation for VirtuOS, but it doesn't exceed 20%. Well, VirtuOS also shares similar goals and ideas with existing approaches, and I already discussed some of the trade-offs in the design challenges. For example, microkernels such as L4, Mach, Minix3, also multi-service solutions which will decompose existing monolithic functionality into separate servers and run them on top of microkernel, such as Sawmill, driver protection schemes such as Nux, microdrivers, SUD. There is also virtual machine-based solutions such as device driver OS or Zen driver domains. VirtuOS uses Zen hypervisor. We adopted a system called dispatch mechanism proposed by FlexSC system, but FlexSC system uses it to merely optimize performance of existing monolithic systems. Similar mechanisms were also used in factored operating system and Core. We believe that novelty of VirtuOS lies in the fact that we use, in combination of system call dispatch mechanisms that we use, as well as virtual machines. In conclusion, I want to reiterate how VirtuOS solved design challenges that I posed in the beginning. So first, that we provide strong isolation. VirtuOS isolates entire vertical slices. It provides separate failure recovery for components, and we can successfully recover from failures. VirtuOS provides good performance, particularly for multi-threaded applications. We provide transparency to existing POSIX applications, as well as compatibility with existing system code. We can reuse existing device drivers in their original form, completely unmodified. Our source code is publicly available. You can see the link on the slide. Thank you, and I will gladly answer your questions.
Richard Black, Microsoft Research. You went into some detail on how the user applications talk to the specialized component domain in the kernel, but you didn't talk very much about how the principal domain in the kernel talks with the driver domains in the kernel. For example, a file system normally interacts quite substantially with the memory manager in terms of operating the buffer cache and pages and all that kind of stuff, and you kind of didn't mention any of that.
Yes. True. This is actually a current limitation of our system, but we expect that we can basically adopt some similar approach which would allow a file system and primary domain to communicate using probably also exceptionless mechanism, but at the kernel level rather than at user level. Did I answer your question?
Kind of, yes.
Hi, Ihor Cruz from NICTA and UNISW in Australia. There's a strong coupling between your applications and your service domains. So if the service domains crash, you generally have to restart your applications. And if that's a file system or something like that, that's going to be most of your applications. Is there a way to reduce that coupling?
Yes, we thought about this. It may indeed be true that if service domain fails, that application will be affected because we keep client states such as file descriptors, for example, and you lose all this information. For example, you can use existing approaches such as, I think, checkpointing. There are also some recent advances. We may try to investigate how they can be applied. But this is also generally true for other systems such as microkernels. So, like, other systems also suffer from this problem.
Mike Ferd from Stony Brook University. Could you comment on cases of doing this copy when you're dealing with very large and arbitrary data structures that you're memory mapping, for instance? So if you mmap a large file and you're accessing something somewhere in the middle, how does your system handle that?
Okay, so first of all, for mmap, we currently did not implement mmap, but mmap can be implemented by essentially sharing the pages of the service domain with the primary, with the user process in the primary domain. So in this case, I guess there won't be any additional copying overhead if you do that. But the problem is that we would have to pin those pages, and this may actually reduce like our ability to basically do some page replacement on this. Thanks.
All right.
I'm Dong Li from Stony Brook University. I have a question about the implementation. So I'm not very clear, is your service domain only servicing a single primary domain, or one service domain might service multiple primary domain?
Well, service domain only service a single primary domain, but we expect that in our design, at least it can be extended so that we support multiple primary domains, and each primary domain will have its own set of service domains.
Okay, so now it's a one-to-one correspondence. So my next question is, we have each kernel data structure for each loadable kernel module, which is actually the driver. Where you maintain the kernel data structure? In primary domain or service domain?
Well, yeah, to be clear, just to clarify it, so both service domain and primary domain, they will run Linux kernel. In fact, we currently use the same Linux kernel, but certain parts will not be used. For example, in service domain, we normally don't run any user processes. We don't, if it's, let's say, storage domain, we don't use any networking in this domain. So does...
My question is, we have a linked list of loadable kernel module data structure in the kernel to maintain a kernel data structure for each module. You understand my question?
For example, can you make an example?
For driver, there's a data structure called struct module in the Linux kernel.
Yes, yes.
I want to know where you maintain such linked list.
Well, drivers will run in the given domain, so they will use the ability of the service domain without any restrictions. So you can just load the modules in the service domain.
Okay, thank you. I understand.
All right. Thank you.